Hello, class. This is Mr. Hart. And in this podcast, we want to continue our discussion of pressures and fluids, and we want to get into more of the mathematics of how the buoyant force works and how it's calculated. Last time we talked about density and kind of this general idea that it's more dense or less dense than the fluid it floats or sinks in. Okay, but let's talk about how the buoyant force works from a mathematical perspective. Okay, but I want to start with a story. Okay. Of a man named Archimedes. You may have heard of this story already, but he is one of the first people that really figured out how the buoyant force worked. I don't know if this story is true or not, but according to legend, Archimedes worked for the king of Greece, or whatever he was called at the time, and he had a suspicion that one of his servants was making his crowns out of gold and silver. He would mix in silver to replace some of the gold and keep some of the gold for himself. So he thought this servant was mixing metals to steal from him, basically. And so he asked Archimedes to figure out a way to determine if his, crowns and all these golden things were pure gold or gold and silver. Okay. And Archimedes couldn't figure it out, but one day he, jumps in the bathtub in the morning, and he realizes when he jumps in the bathtub that he displaces fluid. He moves fluid out of the way. It spills out of his bathtub. And so according to the legend, he was so excited, he jumped out of his bathtub without getting dressed, and he ran into the streets naked and screamed, "Eureka," which means I found it. And so he goes and tells the king, and he puts the crown in water to see how much fluid it displaces and all this stuff. Again, I don't know if it's true or not, but that's the legend. Okay. But the idea is true, okay, and the idea is this, is that if an object is sitting in water, okay, and it needs to float, it has to displace enough water to match its own weight, okay? And hopefully you kind of saw this from the lab that you did with the pennies and the boats, right? As soon as the weight of the pennies was too much and you couldn't move more water out of the way, the boat would sink, okay? So mathematically, we can describe this principle with this equation, okay? So this is the buoyant force, okay, or force buoyant, okay? This is the mass of the fluid. That's a subscript, by the way. It's not very clear in this font, but this is m sub f, okay, times gravity, or gravitational acceleration. So if you know how much, water you need to move, and hopefully you're on Earth, so gravity is always the same, then you can figure out how much buoyant force you need. Okay. This is the idea. It turns out this is a little bit harder to work with because we usually don't know how much mass we have moved out of the way. Usually we know how much volume we've moved out of the way. Okay. So we can write this in a slightly more convenient form by writing it in this fashion. Okay. The force buoyant, or buoyant force, is equal to that density of that fluid times the volume of that fluid times gravitational acceleration. Okay. So in this form, it's a lot more convenient because we usually know the density of the fluid we're dealing with. With water, it's 1,000 kilograms per meter cubed. Then we just have to measure how much volume has been displaced, okay? And then times it by 9.8. Again, the F is a subscript. Remember this number, density of water is 1,000 kilograms per meter cubed, or 1 kilogram per liter, okay? Both of those are useful. And so using this, we just have to figure out how much water we displace, and that determines the buoyant force. So let's try a problem. So an object displaces 3,000 kilograms of water when placed in the ocean. What is the buoyant force on the object? Okay. Well, this is the first form where we say the buoyant force is m of the fluid times g. We've displaced 3,000 kilograms. We times that by 9.8 meters per second squared. Okay. The buoyant force on this object will be 3,000 times 9.8. which is 2,900 or 29,400 newtons. Okay. So we can do that. That's an easy calculation. Usually that's not what we end up with when we actually measure stuff. Usually we end up with something like this. an object has a volume of 18 cubic meters and is placed in the water, what would the buoyant force be on the object, assuming it gets submerged? Okay. Well, we can do the same thing. This time we'll use the second version, the density of the fluid times the volume of the object, okay, times gravity, or 9.8. That will give us, if it's water, 1,000 kilograms per cubic meter times 18 cubic meters times gravity, which is 9.8 meters per second squared. Do all that. And we should get that the buoyant force on the object is 176,400 newtons. Okay? So there we go. So a lot easier to calculate if we know the density and we can figure out the volume of the object or how much it's displaced. Okay? So key idea from last time was the fact that the densities had to match. That comes from the fact that the buoyant forces have to match. So we could also state this principle. Okay? When will an object float? Okay? If the density of the object is less than the density of the water or whatever it is, or if the buoyant force on the object is greater than the weight of the object, it will also float. Okay? And likewise, if it's less than, it will sink. Okay, so there's an amount of buoyant force that can be applied to an object. If it's greater than its weight, it floats. If it's less than its weight, it sinks. Okay? So even a big, huge object like an aircraft carrier, right? Giant ship, right? If you can displace enough water to get a huge buoyant force, get this huge volume on this object, then you can displace enough water to carry the weight of the aircraft carrier and it won't sink. Okay? So that's the big concept I want you to remember, and that just comes from Newtonian physics, right? You know, balancing the force diagram up, down. If the weight is more than the stuff going up, it will sink. You know, it's not a complex idea in that regard. It just comes from Newton's laws. Okay? But I hope that makes sense. We're going to move on to pressure and think a little bit about pressure on objects and how it kind of relates to buoyant force. Okay? So let's talk about what is pressure. Okay? Now, again, I have to remove some of your English terms that you probably have thought of with pressure, like, you know, emotional pressure or anxiety. Okay? Those are English terms. Physics has a very clear, distinct pressure. Okay? There's a definition, and that definition is this. Okay, pressure is the amount of force in a given area. Okay, or we can write it as capital P equals the force over the area. Okay, so this is pressure. This is the amount of force we have, and this is the area it's confined to. So this can be very useful for describing why certain systems behave the way they do. For example, you've probably seen the demonstration where a guy lies on a bed of nails and someone breaks a brick over the bed of nails and it doesn't hurt him, right? The reason that works is because there's enough pressure on the person's back that they don't get injured, okay? Even though nails individually are really small, overall they have a large area. Okay, so area can greatly influence how much pressure you feel or is in a certain situation. Okay, let's think about units for a second. Force is measured in newtons. Area is measured in meters squared. You know, square inch, that type of stuff, square meter. And that unit is what we call a Pascal. Okay, he was a scientist that did a lot with this. Okay, so pressure is measured in pascals, newtons per meter squared. Okay, so let's look at an example. So a man punches a wood block. If he punches with a force of 600 newtons and his fist has a surface area of 0.015 meters squared, what is the pressure? Okay, well, all we're going to say is we know the pressure equals the force over the area. Okay, the force is 600 newtons. The area is 0.015 square meters. We put that in our calculator. And we get that the total pressure is 40,000 pascals, okay, which is quite a bit. So this is, for example, why getting punched in the face hurts so much. It's not that the force of someone's fist is a whole lot. 600 newtons isn't that much, okay? It's that it's being applied to a very small area, okay? In fact, a lot of the reasons why you feel pain is because of the pressure, not necessarily the force, okay? If, for example, you dropped a brick from a meter up onto your chest or your stomach, you probably wouldn't feel that bad. It wouldn't hurt that much because your stomach's a large area. If you dropped a brick on your toe, that's going to hurt a whole lot because your toe is a very small area. It's going to be a lot of pressure. Okay, so the area has a big part to play in this type of stuff. Let's do another example. A .38 special bullet has a cross-sectional area of 0.0025 meters squared. In order to puncture skin, the bullet must apply a pressure of 345.5 kilopascals. How much force does this bullet apply to the human body? Well, we'll do the same thing. We say pressure equals force over area, but we're looking for force this time. So we're going to times by area, and we'll get pressure times area equals force. Okay, which in this case, we know the pressure is 345,500 pascals, and the area is really small. It's 0.00025 square meters. Okay, when we times those together, the answer can actually be quite surprising. We get a total value of just 86 newtons. So the total force that a bullet applies to your body is 86 newtons. Now that is a super small amount of force, but because the area, the cross-sectional area of the bullet is so small, that's why it's able to go through your body and cause so much damage. Okay? So one of the big concepts I want you to understand is that pressure is a factor in a lot of cases, and especially when we're talking about pain. Okay, pain is directly related to pressure, not the force. So that's it for this lesson. Hopefully you understand the buoyant force now and pressure, but just go ahead and make sure to do the homework. Let me know if you have any questions, and thank you for watching.